This is video number 9 for CS2124. I don't know if I fixed the sound. Maybe I just have to talk louder. But anyway, let's continue with the linked list. I think we've got just about everybody except the Destructor and Get. And I'm going to go all the way back and look at the Destructor. Now we know what we've got to destroy. We know all the private variables, all the state variables. I keep using both terms. I'm sorry. But the Destructor, this has got to, I'll write a brief description, get rid of all nodes in the list. And just for emphasis, in case there was any doubt, including the empty head node. And you might have just gasped in horror. Well, if the empty head node's gone, then all of a sudden all our class invariants are going to be violated because the head pointer has to point at the empty head node, the tail and the cursor, they all have to point at some node, and now there are not going to be any nodes in the list. Well, those are the rules. The Destructor gets away with murder. In programming terms, I suppose that's literal. It murders all the nodes. The Destructor is the last gasp of the linked list. It's on the way out. It's getting destroyed. It's going away. So there are not going to be any other member functions that are going to be called on a list after the Destructor. It's cleaning up the mess. So here are the bookends. The constructor gets almost nothing to work with. It's responsible for making sure all the class invariants are in place and true the very first time. All the other member functions, remember, they get to assume that for free, but they also have to ensure that the class invariants are still true when they exit. The Destructor is destroying everything, so it could assume all the class invariants are true if it wanted to, but it gets to break all the rules. It violates all the class invariants because it's on the way out. And now I'm repeating myself. The before picture, since this one is kind of the grand finale for the list, I'm just going to do the whole shebang here. Head, cursor, tail. Head points at the empty head node, just as it always has. There's some yada 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 nodes in there. We don't know how many, we don't care. The cursor points at something, and yada 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 again. And then the tail, which has, oh, there's that missing class invariant I sent you an email about. I hope you read it. The last node on the list has to have a 0 next pointer. I don't know how often we use that, but certainly that's the only safe way to go about it. I'll put some made up data in here. M-U-D. For mud, made up data. See what I did there? Okay. That's the before picture. The after picture. Now you might think the after picture is just going to be a couple of question marks. There's absolutely nothing left. That's not strictly true. The Destructor is our contribution to cleaning up all the stuff for the linked list. Some of it is just going to have to go away automatically when it hits the closing curly bracket. We don't have any way officially or even unofficially to delete the storage that was set aside for our private variables, head, cursor, and tail. And it feels like we're violating our own convention here. There's not even any real compelling reason to set those to 0 after all the nodes are gone, because remember, we're on the way out the door. All this stuff is going away. There is no danger of accidentally re-accessing or accessing again the head or the cursor or the tail as there we go. So we could just leave these pointing around to random garbage ghost locations of nodes. So I'm going to make it look like that, saying that I can leave that garbage and it's not going to hurt anything. Okay? Well, how are we going to do that? Well, that's the only one that's safe to delete right now, right? Without causing a memory leak. So somehow or another we got to run, maybe the cursor, it doesn't really matter, who cares? We could run a temp pointer, run the cursor pointer all the way down to the empty node, or wait, maybe the node right before the last node, and then delete the last node. And then we got to do that again, run all the way down to the end of the list, get to the node before the last node, and then delete that. And I'm making all this up as I go along. It's the first thing I said, so of course it's wrong. There is no compelling reason to delete that as long as we avoid the memory leak. Let's think real hard. You know what? I'm going to change this. M is the first real node in the list. Think about this real hard. We went to all that trouble to be careful to keep the class invariance true and not break anything when we did the remove function, right? Now the remove function can be re-enlisted here to do something more than just remove a single node in the list. Think about this. What if we reset the cursor, which we have a function to do that. What if we reset the cursor to the empty head node? Called move to front, I believe it was. So move to front would move the cursor up here. What if we call remove and we've implemented it correctly? Well, remove will get rid of the M. Not only that, it will patch up the gap, making sure there's not a memory leak. Let me say that again. What if we call move to front, move the cursor to the empty head node, and then turn around and call remove? Then it will get rid of the first real node in the list. And no harm done, no memory leak or anything. What if we leave the cursor exactly where it is, and then we call remove again? It's going to delete node U, and let's pretend that, a lot of pretending going on here. Let's pretend that D is the very next node in the list. Then what's going to happen is, when we remove U, then our remove function, which was so carefully crafted, will close up the gap that was left by deleting node U, and now the empty head node points to D. So what's going on here? I'm going to need both hands for this. What's going on here is we're reeling them in. If we move the cursor to the front and call remove, 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 then one at a time, these real nodes in the list take their turn. They move up to the front like little lemmings jumping off a cliff. They get whacked one at a time. We take it out, get the storage back to the system, and point to the next node. So we can use our remove function just to call that over and over again, and we don't have that horrible thing that we might have to do of going down to the end of the list, then going down to the end of the list again, going down to the end of the list. The nodes that are getting deleted, they're moving up to the front one at a time. I'm not going to do that gesture anymore. So get my notes back here. You got the idea? Look at this picture. What could be simpler? Well, you know what? I'll just go ahead and leap to the steps here. If that didn't make any sense, go back and watch it again. Maybe it will then. 1, call, move to front. I'm going to double underline that. That's not a variable name. We're calling a function that we've already written, or at least in theory we have. We've already designed it. We already know how to do that. So this function, this destructor function, is going to start by calling another function. Oh, but wait, there's more. We set up a loop. While remove, call our remove function. While remove returns true. Call remove, call remove, call remove, call remove. As long as it keeps returning true, what do we want to do? Well, actually, the remove is doing all the work for us. So, very strange here. We could have empty curly brackets. While remove returns true, do nothing. Like I said, remove's doing all the work for us. We just keep calling it. Call remove, bye M. Call remove again, goodbye U. Call remove again, goodbye D. What's going to be the case when remove finally returns false and we fall out of the loop? Well, we've pulled in, reined in all these nodes one at a time. Even D will be gone, and remove will copy the next pointer of D into the empty head node. So that's what we're going to have left. All this mess will be gone. Actually, I made a bigger mess, but all this mess will be gone, and the head will still be pointing at the empty head node, except now it will have a 0 next pointer because all the real nodes in the list have been deleted by the remove function in a loop and a hole in the bottom of the C. As far so good? You read that? Well, we've got one more step to do before we are at the after picture. Remove can delete any real node in the list, but it can't remove the empty head node because remove has to go to the node after the node pointed at by the cursor, and there's no way to back up in front of the empty head node. So that has to be done as a separate step. Delete empty head node. That says head. Delete empty head node. Now, do we have to do the destructor like this? Absolutely not. There's at least one person out there that's already implemented it, and they didn't do it anything like this at all, and it's still perfectly good. I did this on purpose, so I could call a couple of functions here. Move to front, call remove. This is an example of what we in the biz would call a composite function. C-O-M-P-O-S-I-T-E function. Composite function just means you spare yourself some work and call some functions that you've already written. We've already got move to front, so there's no reason to do anything special to do that. And member functions can call other member functions. They're all inside the same club. They can all see each other. They can all see the private variables without doing anything special. So this destructor, which is a member function, can call move to front if it wants to. Doesn't even have to specify which object because we're inside the object. Then it can call remove over and over again in a while loop. While remove keeps returning true, just keep going, and one at a time it knocks off all the nodes. So we're, instead of coming up with some complicated algorithm to delete the nodes in a particular order or whatever, we just use functions we already got. And that's a composite function, where you take advantage of things that you've already done to simplify doing things that you have to do next. I've used up the whole board, and that's the destructor. It's just in my nature, I can't help it. Are there any questions? If there are, please write them down and bring them either to office hours or our last class meeting of the week. Bye-bye, Destructor. I'm destroying the Destructor. All the storage is gone, and now all the words and pictures are gone. In just a minute. Takes a while. Nice weather we're having today, huh? Makes you want to go outside and play. Just don't play anything where you have to be around anybody. Those are the rules. I think get was number 5. I meant to go back and check my notes and I forgot to. The get function is the only one remaining. It's special in more than just being the only one remaining. It's our one and only accessor. A-C-C-E-S-S-O-R. Why is that important? Well, it just means that the get operation is not allowed. Not only should it not alter the linked list, it is not allowed to alter the linked list. It can't change the order of the nodes, can't change head, cursor, tail. All it can do is look at this stuff. And also, it's going to have a precondition. Precondition is cursor points at the node that precedes the node to read. Cursor. Remember, the precondition is something that the main program is responsible for doing. So the main program's going to have to call move around or whatever with the cursor to get it right where it wants it. Cursor points, abbreviated points, points at node that precedes the node to read. And that's not part of the algorithm or the picture or anything, so I'll put it in little square brackets like that, both sides. Cursor points at node that precedes the node to read. And remember, in cyberspace, nobody can hear you scream, but I can read your mind. Why on earth? E-A-R-T-H. Question mark, exclamation point. We finally got to an operation where it makes sense to just use the cursor itself, for crying out loud. Why don't we just return the data that's at the cursor node? Here's a picture. Here's a fig. It's not before and after. Well, hang on just a second. I was about to say something that wasn't really strictly correct. Cursor points at this node. I'll give it a G for garbage. And G points at D for data. Yada, 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 all the way down. Now, here's the why on earth. The why on earth, why don't we return G? Why don't we return what cursor points at? Well, it's sort of a strange sort of reason. Answer, since I didn't leave any room whatsoever for the answer. Yet another term. We get at least 2 new terms per video, don't we? By internal convention. I-N-T-E-R-N-A-L. Convention. You know what conventions are. Internal convention means that it's an algorithm or design convention that it's like an inside joke almost. It's a secret for whoever's implementing this class to always do it the same way. And here's what I mean. This kind of L shape going on here, the cursor points at some node points at the other one. To convince you even more, I'm going to whoop out the gold for a gold star. This node right here, man or woman of the hour. Node D, that's where all the focus has been in every single operation up to this point. We insert a new node, that's where it goes. We remove a node, that's where it comes from. All the other operations use this L shape. Nobody uses the cursor node. Everybody uses cursor arrow next. So why should we be rogue and go out and be different about it? The answer is, it's not a good idea to do that. If everybody sticks to this internal convention and the node of activity, the node of focus is always cursor arrow next, then we've just got less to remember. It's going to be easier to keep all of our member functions consistent with each other. Because everybody's using cursor arrow next. Nobody uses the plain old cursor node. Now, there's an even stronger reason than that. If we do return the value or we read the value of cursor node, cursor arrow data, then we're going to have to check and make sure we're not pointing at the empty head node. At the moment, the way we've implemented get, or the way we're going to implement get, is we get cursor arrow next, and if the cursor points at the empty head node, then we are not accidentally going to return garbage. We're not going to read the garbage out of the empty head node. The first node in the list that will even be accessible to our accessor, our get operation, will be the first real node in the list. So imagine a question mark here, cursor pointing at the empty head node. Then the first node that we could possibly get the data from is cursor arrow next. I really need people to ask questions and raise hands and make comments to keep me from drifting off into an infinite loop of saying the same thing over and over again. But at any rate, bottom line, cursor stays one behind the node of interest, no matter what the operation is. There. Oh, and this, by the way, if I'm going to stick to my own internal convention, then I need before and after pictures. But you know what? This is not only fig. This is before, and this is after. You might very well want to visualize what you're working with in an accessor, but if your before picture is different from your after picture, then you've got a problem. You've done your design wrong. The accessor is not allowed to change the list. So whatever we've got coming in has got to be exactly the same as what we got coming out. Now, as we do the steps, rather than lead you down a murky, dark path and say, well, let's do this, and then we find out we can't do that after all, let's just go ahead and see if we can be deliberate about it and look ahead and see if there are any possible special cases, those pesky boundary conditions that we better keep our eye on. I've already gotten rid of one, right? If we called move to front right before we call get, then we don't have a problem. Call move to front and call get, what you're going to get is the data of the first real node in the list. It's not going to accidentally get the empty head node's garbage. So we don't have to worry about that. What about the other end? What if cursor is pointing at the last node in the list, and we've gone back and made sure we've observed the class invariant that the last node always has a 0 pointer? Then, yeah, we might very well have a problem there. So there is a way this operation could fail. By convention, since there's a way it could fail, we want to detect that right off the bat and return false and get out of here. How could this fail? One, if there's no node out there, if cursor arrow next equals 0. I won't put equals. I'll say is. We're talking pseudocode here. If cursor arrow next is 0, then return false. There's no node to get, can't get. Let the main program or whoever called me, let them know about it. If we're still here, we've got that implicit else, but we get to assume that cursor arrow next is not 0, and by our own conventions, that means it's got to be a legit value. So what we'll need to do here is copy cursor arrow next arrow data all that long list, cursor, arrow, next arrow data, the D in this picture, to a reference parameter. And an unnamed variable. I think, well, of course it has a variable name in the header file, but I didn't review that either, so I don't remember what the name of it is. It's probably something like item. Yeah, I think that's it. Into a reference parameter, comma, item, I'll call it. Now, item, for an accessor, for this accessor, our item reference parameter for that function is not providing needed information to this function. What it's providing is a place to put the data. So it's being sent in as an empty box to be filled in by the get operation, which should take the, in this case, the D, and copy D into reference parameter item so the main program can find it when we get back with the return value of true. Return true. Because we were successful. Now, I don't know if this has irritated you. You might think, well, it's just so natural that we would get an item and return it. Get an item and return it, and yet we're not doing that. We're getting an item and putting it into a reference parameter that seems unnecessarily complicated. Here's our problem. We want to be able to handle anything that comes at us. We want to be robust, ideally bulletproof, unbreakable. So we've got to cover the case where we might not be able to get an item. We've got to make sure this doesn't crash our program. So we can't just mindlessly return cursor arrow next arrow data because there might not be any data out there. So you can think of it this way. The return value is already taken. We got to get that data value back to the main program some other way. So that's why we're going to pass in the reference parameter, fill in the blank, and then return true. A convention that I didn't write down, I don't believe. This came before spring break even. If there's any way a function might fail, you had one job and you couldn't do it, then we return a Boolean value, true or false, to indicate true or false back to the main program so it knows whether or not the operation it wanted to do was successful. Okay, you know what? I think that's all of them. I'm going to put a done box down here. Done, period, box. And unless you can think of something to bring up during office hours of the special class, check this one off. Could it be? Are we actually done with the linked list? I hope so, at least for a little while. I'm going to follow hot on the heels of video 9 with a video 10 that discusses a little bit of the implementation concerns for program 6. So after you get all this one down, you might want to go ahead and look at that so that you can get going on your program 6. But until then, I'll see you online.